right, so when we first started this chapter, we talked about heterogeneous mixtures. Today we're going to move to the other side of those mixtures in that diagram that we had, and we're going to talk about homogeneous mixtures. Homogeneous mixtures, the prefix homo means the same, and so a homogeneous mixture has a uniform appearance all the way through it. It doesn't matter if you take part out of the top or part out of the bottom, it's going to look the same all the way through. Very unlike trail mix, where if I just reach in blindfolded and pull out one piece out, I might get a peanut, and the next time I reach in and pull something out, I might get a raisin. With a homogeneous mixture, if I reach in and just pull out a small sample each time, it would be the same no matter which part of that mixture I pulled out. Most commonly, a homogeneous mixture is also called a solution. Now, we tend to think only of dissolving a solid in a liquid to make a solution, and those are very common examples. So like if I put salt in my water if I'm going to make pasta, that's an example of a solution. If I put sugar in water, I love to feed the hummingbirds, and so I make a solution of sugar and water and put it in my hummingbird feeder so I can watch the hummingbirds in the spring and summer. So those would be solutions of a solid dissolved in a liquid. But there's all other kinds of solutions as well. You can dissolve a gas in a liquid. So when you open a soda pop, you've got carbon dioxide dissolved in that sugary water, and that is what gives soda pop its fizz. Once the gas maybe kind of escapes from it, you don't really like your soda pop as well because it's flat. You can dissolve a liquid in another liquid. An example of that is isopropyl alcohol, which if you go to the doctor and they are going to give you a shot for some reason or other, the medical assistant will normally rub isopropyl alcohol on the spot where she's going to give the injection to make sure there's no bacteria that she's going to inject in with the medicine when she puts it in. So isopropyl alcohol is an example of a liquid in a liquid. You can dissolve a gas in another gas. The air that we breathe all the time is mostly nitrogen, and there is oxygen dissolved in the nitrogen. Now, the way you think about that is whatever is there in the most abundance would be, that's what you considered what it's dissolved in. So since the nitrogen, there's way more nitrogen in the air than there is oxygen, you say the oxygen is dissolved in the nitrogen. You can also dissolve a solid in another solid. Again, we do this when we manufacture certain kinds of metals. I dissolve carbon in iron to make steel. You can also dissolve tin in copper to make bronze, and this is often called an alloy, where we put those two things together as a solution to make them stronger. Iron is strong, but if you dissolve carbon in it to make steel, that's even stronger. And so those alloys are very beneficial to us. Now, the question is, how does this solvation process work? And we're going to specifically focus on how water dissolves something because we see water dissolving things all the time. So let me make a little bit more space up here. And we're specifically going to talk about how water dissolves salt. So if you remember, salt is sodium chloride, and what happens with the sodium chloride, it forms an ionic bond, which basically means that you have a chlorine which has 7 electrons and sodium which has 1, and so I gave it 8, didn't I? Sorry about that. So your chlorine has 7 electrons, your sodium has 1, and so this electron just gets donated to this chlorine. So what I end up with is a sodium ion with a positive charge and a chlorine ion that has a negative charge. In reality, it's got those 8 electrons in its outer shell, but just for simplicity's sake, I'm not going to draw them all right now. So when you have salt as it comes out of your salt shaker, and you've got all these little particles of salt, what that really is it's a complex of, remember that positive and negative charges attract one another. So the positive sodium is attracted to the negative chlorine, which is going to be attracted to another positive sodium, which is attracted to another negative chlorine. And so what this is then is a lattice or a network of all of these different ions that are just being held together by an electrostatic attraction. So a chunk of salt, if you could look at it down on the atomic level, would look something like this. So you take your salt and you sprinkle it into your kettle where you're going to make pasta or whatever else you happen to be doing. And so what happens then is you have your water molecules. Now you remember the other day I told you that a water molecule looks like this. Got his extra two little electron pairs up here. This is a partially negative charge, and remember these are partially positive charges on my water molecule. All right, so what happens is that as you put it in, and if the water's boiling, the water molecules are moving all over the place. If you put it in and you stir it, you're moving your water molecules around. Even if you don't do those things, the water molecules are moving anyway, because remember, we said molecules are always in motion. And so the water molecules start banging up against these particles of salt that are in here. And what happens then is that if the water molecule happens to come in from this direction, with this negative side pointing toward the salt molecule, what is it going to be attracted to over here? If this is a negative charge, it's going to be attracted to a positive charge. And so this partially negative oxygen is going to be attracted to a sodium molecule here, maybe one over here on the side. And so what's going to happen then is, because this is on the edge, it's going to have water molecules coming at it from this direction, it's going to have water molecules coming at it from this direction, and they'll keep banging at it long enough until it gets enough water molecules. And remember that when we do this, we actually have to think in 3 dimensions. So I could draw another water molecule coming at it from this way, but because it's 3 dimensions, there's going to be water molecules coming from in front of the board, there's going to be water molecules coming at it from behind the board, and eventually the attraction of these partial negative charges will attract this partial positive charge, and it'll just pull that sodium atom or that sodium ion right off of there. Then you're going to have a sodium ion that's kind of broken off by itself, and it's going to be surrounded by water molecules that all have their oxygen pointed toward that sodium, because opposite charges attract to one another. Okay? So the water molecules have pulled this guy off of here, and then they completely surround him like this. Now what you've got here is I've got chlorine that's going to be more exposed. I've got chlorine exposed here on the corner, but this time the water molecules are going to orient themselves the other way, because this negative charge is going to be attracted to the positive charges on the water molecule, because remember, again, opposite charges attract. So this time the water molecules are going to be coming at it from this direction with the hydrogens pointed towards the chlorine, and they're going to start banging into it and starting to pull that away. And so again, eventually what you're going to have is you're going to have this chlorine ion in the middle, and then you're going to have the water molecules completely surrounding it like that. I didn't draw that very well, but I think you get the idea. And then I'm going to have water molecules on this side, like this. Another one up here. And remember, it's in 3 dimensions, so there'll be a water molecule out in front of the board, there'll be one back behind the board. These ions will be completely surrounded, chlorine ions will be surrounded by water, such that the hydrogen ions are pointing, or the hydrogen molecule is pointed toward the chlorine, that part of the water molecule, so that the opposite charges are attracting. Eventually, all of these little ions get pulled apart by the water, and every single ion is going to be surrounded by these water molecules this way. So we said that water is a polar molecule, and we know that this is going to have an ionic bond in it, and because these charges are attracting each other, what that means is that if I have something that's polar like water, a polar solvent, the thing that does the dissolving, the solvent, so water would be the solvent, the polar solvent will dissolve an ionic compound like salt, or because Other polar things are also going to have charges on them. I may have a polar solvent that's going to dissolve another polar compound. So that's, a lot of times in chemistry, we say that like dissolves like. So since polar things have partial charges on them, they're going to dissolve other things that have partial charges on them. If you have something that doesn't have any charges on it, so like we talked about vinegar and oil dressing, those, they don't dissolve. They are going to keep separating. And that's because oil is not polar. It doesn't have any charges on it. So a polar solvent will not dissolve something that's non-polar, something that doesn't have charges on it. Okay, so something that's polar will dissolve ionic or polar compounds. Something that's polar will not dissolve a non-polar compound. Okay, and so that's called the like dissolves like rule. Okay, so the next time we get together, we're going to go into a little bit more detail about water and some of the properties that it has. So, but today you kind of have an idea now of why water does such a good job dissolving things.